So here I'm going to present a project we did some time ago on the emission zone of gamma rays on the magnetosphere of dipolar pulsars. The main motivation of this work is that in the literature in the recent decades, it has been reported that gamma rays specifically are very sensitive to the structure of the magnetosphere of these objects. And the question to answer would be, where on the magnetosphere does this emission zone is exactly? Well, this is a very hard question to tackle. I am going to present just the first approach to answering this question. Well, as I said, I'm going to structure this talk, first talking a little bit about pulsars and neutron stars, then the dipole model of pulsars, and some debate in the literature on the emission zones that come of gamma rays in these objects. First vacuum, and then I'm going to talk about a little bit more on the force-free approximation of electrodynamics, which is used inside the emission zone, the emission model called separatrix layer, which we are using to limit or to bound or narrow down this emission zone. Okay. So first of all, as all of you know, pulsars were discovered in 1968. Jocelyn Bell was analyzing data from radio telescopes, and she noticed this very pattern-like pulse pattern in radio waves that comes from various objects in the universe, and they were quickly identified as rotating neutron stars. So essentially, what neutron stars are very compact objects with radius of about 10 kilometers long, with masses similar to 1.1 solar masses, even to 2.1 solar masses, which also that is debatable. And the most important things about these objects is, well, the most important feature of these objects is that they are equipped with very strong magnetic fields, ranging from 10 to the 9 Gauss to 10 to the 15 Gauss. And well, in order to produce this observation that Jocelyn Bell did, they need to rotate at very high speeds. You know, they have to have periods of about milliseconds or even lower. So the dipole model of pulsars is the first approach to model the magnetospheres of these objects, and they are modeled as a vacuum dipole with a magnetic field following this structure. That comes from the multipolar expansion of the vector potential, as all of you know. And here in these slides, I would like to introduce some definitions. So first of all, a magnetosphere is the vicinity of an astrophysical object that where charged particles can interact with its magnetic field. The light cylinder is the boundary at which co-rotating particles with the star can co-rotate without surpassing the speed of light limit. And the magnetic field lines in this talk, we're going to classify them as closed here in blue, as open here in red. Of course, magnetic field lines are strictly closed always, but in the literature we call open magnetic field lines those that close beyond the light cylinder limit. And the last open field lines would be the ones that are just tangent to this boundary of the light cylinder. Okay, these are associated or have a close relationship with the separatrix. The separatrix is the boundary between open and closed magnetic field lines. Okay, so these definitions are important. And here we are seeing the dipole model with the dipole vector and the omega vector, which is the angular velocity vector, and the angle between those two vectors, we're going to call it alpha. And this is going to be very important in our results. Okay. So strictly speaking, alpha can vary, and okay. Other important definitions are the polar caps. The polar caps are the part of the surface of the star from which open magnetic field lines emerge from. So it's all of this surface, and here I'm plotting just the rim of the polar cap, which is where the last open magnetic field lines emerge from. So that's important of the polar caps, and we parameterized or we classify the different types of magnetic field lines using these uh, open coordinates called ROV and the azimuthal magnetic angle. So in order to identify a given set of magnetic field lines, it has a ROV associated to it. If ROV is equal to 1, we are speaking of the polar cap rim, so all the last open field lines. And if we are saying ROV less than 1, we are locating ourselves in the rings. These are called the rings. And from where open magnetic field lines emerge from. Okay, if ROV is bigger than 1, we would be looking at closed magnetic field lines. Okay, saying that, it is nowadays very widely accepted that the pulsar magnetosphere should be dense. And the first approach was a long time ago by Goldrich and Julian, just modeling a simple conducting sphere rotating, equipped with a magnetic dipole field, and from which an electric field would be induced near the surface of this star, pulling out charged particles and populating this magnetosphere. So if you compare the electric force produced by this induced electric field with just the gravitational Newtonian pull, would be 10 to the 12. So every charged particle would be populating this dense magnetosphere with these strengths of magnetic fields and these periods. Okay, at this plot, we are looking at a color plot of the electric charge density of one of our simulations, and the arrows represent the magnetic field. The color ranges from blue in negative charge to red positive charge, and we are looking at the case where alpha is equal to 30. Okay, here the units of distance are in radius of the light cylinder, so the light cylinder would be right here. And as you can see, there are regions close to the star that have a really strong electric charge, either negative in these parts or positives. Okay. And it has been throughout the decades a theme of debate where exactly, first of all, what is the structure of the magnetosphere, if it is a simple dipole, if it's more complicated than that, or also what part of the magnetosphere where electric particles accelerate enough to produce gamma rays. Okay, so here I'm just giving you a glance of two examples of a vacuum case scenario. These two models are called slot gap and two-pole caustic. And let me focus your attention in this model of two-pole caustic. So this model essentially is using a rotating magnetic dipole field, and it assumes that the radiation occurs here near the last open magnetic field lines. In this region, they denote with dashed line. So they are, it's a proposal, and I am taking advantage of this plot to also mention you this angle of observation will be important in order for us to read the sky maps or the results of these two models, sorry. This is another example of the vacuum case where they propose that the emission occurs here in this part called slot gap. I'm not going to give details of these vacuum cases, but just giving you a glance, that it is a well, it was a hot topic some time ago. At looking By looking at the results of the models, one can say if it's a good model, or we should discard them. One of the most important characteristics of these pulsars that emit in gamma rays is this two-peak structure in these plots that I'm going to call light curves, which are essentially histograms of photons in the y-axis and phase or time in the x-axis. All right, so that's a plot of light intensity which a telescope would measure from a given pulsar, right? So this psi represents the alpha angle we were talking about later, and this is the angle of observation. And as you can see, this slot cap model can reproduce this very characteristic thing of gamma ray pulsars, which is this double peak feature. Okay. Very weird to pass 0.8 volts. Yeah, it's normalized. Yeah, the maximum is here, so it's normalized. Yeah, yeah. These are other results of two-pole caustic, and this is an example of what I'm going to call a sky map in this talk. The sky map is similar to a light curve, but it has an information of varying the angle of observation, right? So this is a light curve with an angle of observation of about 50. So one read the sky maps like this horizontal line. So we are reading this horizontal line. You can see the first peak that corresponds to this first peak. The second peak corresponds to this peak, and the other two are right here. So the sky maps are like an enhanced light curve, okay? And this model can reproduce somewhat well the two-pole, the two-peak characteristic, but we're going to see that it has some flaws. Well, this is a comparison between telescope and the model of two-pole caustic in the Vela pulsar, which is fairly good. It can reproduce the two peaks, but as you can see, the second peak is not as good or as accurate as one would like. Okay, so that's like an empiric evidence that these first models are lacking something. Then later on, Bios-Pikowski showed that these vacuum models have some flaws, in the sense that they present large uncertainties in their predictions. By uncertainties, I mean that the magnetosphere structure and the polar cap shape, this polar cap shape is very sensitive to the structure of the magnetic field lines near the light cylinder, because that's how we construct the polar cap. So the structure of the magnetosphere or the polar cap shape, if it is changed just a little bit, the prediction of these models stop functioning that well. As you can see, this is these are the light curves for I think the two-pole caustic case, where one can see the different predictions just by varying a little bit the magnetospheric structure or equivalently the polar cap shape. Okay, so these vacuum models, and they did a complete study of various vacuum models, seeing that, for example, it no longer reproduced this two peak characteristic that is very desirable in our models, because almost every pulsar that emits gamma rays presents that feature. So as a first approach, now seeing that the vacuum case is not the best, one could start by looking at the ideal magnetohydrodynamics. Now, this theory that uses a perfectly conducting fluid, there's no resistive dissipation, and the electric field vanishes. Okay, one can see that the ideal magnetohydrodynamics plus the mounting ourselves in the co-rotating frame. No, sorry, that's not the case. Just from magnetohydrodynamics, one can reach this induction equation, this new induction equation, which depends on the magnetic field and the field velocity. So given a field velocity, one can see the evolution of the magnetic field, and that's why, that is the equation that some codes solve in order to get the magnetic field evolution. The force-free approximation of electrodynamics is the low initial limit of this magnetohydrodynamic theory. And as I said, it's a first approach. Here, it is a good approximation because, well, a fairly good approximation because the magnetic field is very strong. So the dominant force in this system would be the magnetic field. And in this theory, well, charged particles reach an equilibrium point where the Lorentz force vanishes locally, which is represented by that equation, as you can see. So that first approximation allows, allowed by Spikowski to make one of the first non-vacuum cases of simulation, numerical simulations of the magnetospheric structure, and then propose their model of separatrix layer, supposing this force-free approximation, and noticing this very important feature in this model, which is called the current shift. Oh, let me move that. Yeah, the current shift. So as you probably all know, it's a very widely known characteristic in magnetohydrodynamics, this magnetic recognition through currents, okay? And in this model, one can find that this combination of vectorial products of the magnetic field and the field of velocities of the plasma is the electric current density in the co-rotating frame. Okay, and one can find that this thing is just collinear with the magnetic field, making it a simple equation here, where we can see the relationship between the magnetic field here with these approximations and the co-rotating electric field, density, okay? Electric current density, sorry. Inside this separatrix layer model, what they propose is by finding this relationship between the magnetic field and this electric current, they associate this lambda with what I call the current shift, and therefore they assume that the acceleration of particles or the emission comes from the current shift, okay? The structure of our work was taking numerical simulations that come from a code called Onion that solve the electrodynamics, for the force-free electrodynamics in the vicinity of the star, and they give as an output the electric field and the magnetic field. Then we plug these results in our code called XSky, which finds the polar caps, integrates the magnetic field lines, and computes and projects lambda, this function which is associated to the current, and the electric density, the electric charge density. And using that relationship, we can delimit this emission zone inside the model of separatrix layer. So here are some plots of validations of the code, and what I'm showing you here first is in color map is the function lambda, which goes from negative blue to positive red, and the case where alpha equals 0. Okay, both plots correspond to the case alpha equals 0. Here, the mu vector is pointing towards us outside the screen, and in this plot, the mu vector is pointing vertically. It is aligned with the omega vector, So it's called the aligned case. In this plot, we are plotting the polar cap rim, sorry, and as you can see, there is electric current entering at the center and electric current going outside from the polar cap rim. All right. This corresponds to the strong current layer and the current sheet. I'm going to call it old current sheet. So the current sheet in these plots is the part where the color is more intense. As I said, blue represents negative current and red positive. Okay, so this is a very visual test of where this current sheet is, equivalently where this emission zone is. But it is just visual. Yes.
So, to me, or this is virtual.
The simulation were performed in 3D. I didn't make them, but we're just using it, and then I'm just projecting in the plane.
This is exactly what we're or this setup.
Uh, well, I'm taking the 3D data, and then I'm just like cutting in half and just plotting, projecting in the plane. But it is the data that come from the 3D simulation.
So it's not to correlate. It's just to
To correlate them, this sphere should go like this. So you should spin it like this. Here the mu vector is pointing outward, and here the mu vector is pointing that way. So this is red. This red corresponds to this red light that is going outside from the star. Yeah, it's like cutting this sphere in half.
maybe I already asked for another.
Okay.
Question is do you know that the power? So it's not clear
Okay.
information of current.
What you say is clear information of a current sheet.
Because for this corners, then if you have post,
Yeah.
it's not clear to have X points over there. So you have a zoom in.
Oh, so I think I didn't understand the question, but uh, maybe like by looking at this relationship, we're plotting lambda, and it corresponds where the current is like more intense. So it's just saying that the current sheet is near this intense current part of the magnetic field.
So you have using this criterion to say that.
Yeah, and inside the model also. This is the case where alpha equals 60. As you can see, some things change slightly, but well, one can see that the intensity of the entering electric current varies, and it like migrated a little bit up. And in this case, here is the mu vector, and here is the omega vector. So the pulsar is spinning this way. And we can see that it is also highly sensitive, the structure of this current sheet with the angle alpha, like the first result. Also, the magnetic field structure is different, and it is a partial result. Inside this particle model, as I said, they associate certain magnetic field lines with the current sheet by just plotting and observing those magnetic field lines that lie near this big lambda zone or these large lambda zones. So this is a plot on 3D where they plotted with a degree of transparency the lambda function and the magnetic field lines. And it is not very easy to identify the association as you can imagine. So we came up with a numerical criteria to to say or to differentiate between the magnetic field lines which are associated with the emission and those who aren't. So, okay. This using the same XSky code, we can integrate the magnetic field lines. There's a plot of the magnetic field lines in points, and we can determine the value of lambda in every point in every magnetic field line. So we use two criteria that I'm going to explain alongside this talk. The first one is easy, is the weak criteria, which is just saying that lambda has to be larger than a minimum bound. So if a given point has a lambda larger than that, is we store it and we say this point of the magnetic field line is associated. Then we look at sets of magnetic field lines, and as you remember, I I use different sets of magnetic field lines with that coordinate ROV. Okay. To determine the lower bound of the lambda function, we did some plots like this. Here we're looking at the corresponding case of the sphere plot. So here the mu vector is pointing outwards, and we are seeing the case where alpha equals 30. And we plot using the plane quadrants the value of lambda. Just the value of lambda here is in code units, but one can see that the first quadrant and the third one, we observe like a very important jump in the value of lambda. So we can definitely say that if lambda equals, for example, 0.5, we are essentially in the current sheet. So we are here. And in the x-axis of that plot, we're plotting the radius of the light cylinder, which is more or less about this radius. And one can see that this plot tells us that the value of lambda here in the current sheet, which corresponds to this intense color part, is more or less bigger than 0.5.
That's
See,
how are you measuring this lambda extent? Any too long, the great
that's,
different patterns.
yeah.
At least two should be in the same, should show the same enhance.
Yeah, exactly. It is here in the dashed lines with, I don't know the colors, but here and this one are like overlapped. And
Okay.
here, these two are overlapped down. Okay, so
This is the
no, it's compute just alongside the radial directions,
okay.
divided by quadrants, for it is compute.
Can it is a scalar of its own quantity?
Yeah. Then we plot the entire number of associated points, so those who have a big enough lambda, for every case of the alpha, and we say, well, just by plotting them, we can see what coordinate ROV is more or is less associated with this current sheet. So for example, if you see at ROV equals 0.96, one can say is the most associated set of field lines. So just for you to recall, we are looking at if ROV is less than one of the rings. So one of the strictly called open magnetic field lines, not exactly the last open field lines. And our criteria is that those points, those set of magnetic field lines, which are who have at least half of the points associated to the maximum, we call them associated, and they correspond to what Baez-Pikowski visually reported. This is like the biggest, well, the central result of this talk. which is the central results varying the angle alpha and plotting all the number of associated points. So as you can see, first the behavior of alpha is that if alpha is smaller, we have a bigger amount of associated points, and if lambda grows, the number of associated points like decays. Okay, and then we can say, given a set of points in alpha, what set of magnetic field lines are associated with each case. So, for instance, here is the 60 degrees case where I showed previously, and for example, the 30 degrees case is like this. So one say that the associated points range from 0.85 to more or less 0.95. So we have found like these ranges of ROV magnetic field lines, which are associated to the magnetic field and therefore associated with the electromagnetic radiation of gamma rays. Okay, I think that's now for that. And the conclusions is that we contributed to delimit these emission zones inside the theoretical framework of the separatrix layer model, which uses a bunch of approximation of magnetohydrodynamics, which are fairly good, but it's debatable. And we have found a dependency on alpha first, given the change of morphology of the current shift with the inclination angle. And well, this project could be complemented in the future by performing these sky maps and comparing them to the literature or to the observations. And another idea is to use these criteria in binaries or more realistic magnetic field lines or magnetospheric pulsars. Yeah.
Thank you very much. For questions, points. Thank you very much, Axel. Can you please go back to the slide where you were showing your lectures? I wanted to understand a little bit more.
What slide?
I think first,
This?
when you were introducing like the two peaks or one,
Ah,
it could be any.
okay.
So you basically are saying that you have this emission from these two caps.
Mhm.
So this is why you get the two peaks, and you're considering pulsars, so you're getting the emission from them, or what does that mean? Is not having this.
Could you repeat?
Yes, you have these two peaks.
Yeah.
Spikes.
Yes.
And you basically are saying you're getting in the highest spikes I would say the radiation from these two caps.
Yes.
And in principle, you are considering just the polar magnet, but these two caps are antipodal.
Yeah. Yeah, they come, well, it depends on the model, but they come, from each magnetic pole, essentially. So that's why we see that pattern, right? Like if you have like two jets and you like spin, you can see those two peaks. Yes. The color ones? Is that a model? I mean, your program, gives you a 3D one. Yeah, so the data that the program gives us an output is lambda as an array of X, Y, and Z. So we have the three coordinates. I am just plotting, just projecting I'm just plotting the parts of the mu of the mu omega plane. That's just the mu omega plane. Yes, yes. We had like some attempts at plotting something like that, but personally I didn't understand them or didn't like was able to say, but just looking at those kind of images to say these magnetic fields are associated or not. Yeah. The code to run, I think. As part of this project, I parallelized this code and we reduced the time, I think, uh, half or even more, but maybe 15 minutes or something like that. Yeah, 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 yeah. Uh, the force field electrodynamics. Okay. Yeah. Yeah, yeah. Okay. Well, someone else, more questions. Yes. So, which model did they use? Because they don't perform the simulation, but the data for the neutron star, yeah, was the radius, the mass, right? Because I see that it depends on the angle in your glass plot. Yeah. It depends on the angle that you see. And you measure different radius for the neutron star. So is that comparable to what they take from the initial data? Yeah, I don't really have the details, but I would guess that we need first, as you said, and well, the velocity at which the plasma is rotating with the star and all of that. But I don't have the details on the other things. So, but of course, I would think that it uses the mass or the radius of the star. Your last the number point. Ah, okay. You can see attendance when you increase the angle, it goes to the right and lower. Oh, yeah. I- But the angle of 60 and 90 are almost the same. Yeah. Well, the peak is almost in the same point. So yeah, they are similar. But well, first, these ROV coordinates are normalized to the last open magnetic field lines. So uh, we're just comparing different angles for the same star, essentially. And yes, one can see like I didn't put all the plots corresponding to 30 and 90 here, but as you can see, there's this trend. And also another trend is that the current sheet that is connected to the star, so the connection from here to the surface of the star by this, which is called in the literature strong current layer, uh, uh, is how do you say, it gets lower by increasing the angle alpha. I want to make sure well, did you say you don't have a pre-electrons in there with the magnetic fields? Well, in nature, it is expected, but here in this model, we are just looking at the force-free approximation on magnetohydrodynamics. So we're not speaking of particles or nothing. Yes, no, we're not using particles. Technical was I think interesting in reconsider like in things electrons, maybe you have to consider any other analysis for the oh yes. Yeah, these models do not enter like head on emission mechanisms, but well, they suspect they come from curvature radiation or inverse Compton and those mechanisms. Well, as I said, this model or these simulations, I don't know if they contain a given mechanism to produce this radiation. I wouldn't think so.
Okay, I have another question.
Okay.
Last.
Yeah.
And last question regarding to particles. Maybe you can use results from particle cell simulation
Okay.
because we have electron distribution function. So basically, you need only to know what is the magnetic field.
Okay.
Works. And then maybe Goldrich Julian density you introduce, and then with that you can know what is the energy of the electrons.
Oh.
This is one thing, and then the open question is how then you associate the current shift or magnetic field intensity to the emission from the
Okay.
pulsars, because you have motivation from observations. But then the question is, if you don't have particles, if you don't have radiation mechanism, you only have magnetic field.
Yeah.
And we know that from current shift, if a particle passing there, it's gaining energy.
Yeah.
But then how you associate this to the emission? It's open question.
Okay.
Think about that, and then
Yeah.
we can discuss later. Yeah.